Hello. I think I got rid of the waiting room, so I think everyone will get in right away this time. Okay, waiting while everyone enters. Okay, most people are here by now. Okay, I'm going to go switch to screen sharing. Okay, you should see my screen now. Okay, does everybody see the screen? Did everyone hear me? Everything seem okay?
Yep.
Oh, okay.
Yes.
All right. Here's the okay. So here's okay. Here's what we're going to start with today. We're going to start talking about the input data structure to the render. Okay, so there was a reading about that a little bit, and most of what you need to read is in the README. Okay, let me download this render. Okay, download it to my desktop. Let me extract it. Okay, get rid of the zip file. Okay, so so far, the render is in here, and we've been talking about the frame buffer. Okay, the frame buffer is the input to the render pipeline. That's the algorithms. And I'm sorry, the frame buffer is the output from the rendering algorithms, which is the pipeline. And today we want to start talking about the scene package, which is the input to the rendering pipeline. And after we talk about the scene package, we'll talk about the pipeline itself. Okay, and if you look at this README, your homework assignment is about the output data structure. That's this guy. Today we're going to start talking about the input data structure, and next week we'll be talking about the key idea, the rendering algorithms. Okay. All right. Now, first, does anybody have any question about your homework assignment is about the frame buffer? And we've been talking about the frame buffer for the last few times. Does anybody have any question about any of the stuff that's come up with the frame buffer or about the homework assignment? Anything, any problems or anything weird or anything somebody's not sure about? Okay. As usual, if you have questions, send me an email. Yeah, let's see. The homework assignments due when? I forgot already.
Tuesday.
Tuesday, the 8th. Okay, yeah. So, and the next homework assignment will be about this data structure. Okay. So the current homework assignment is about this one, and the next one will be about this one. Okay. So if you have questions about the homework and stuff like that, please let me know. Okay. So we want to talk about what goes into the rendering algorithms. Okay. So here's kind of the key idea. Let me see if I can get a nice picture. When you have a picture like this, artists call these still lifes. Okay. From a point of view of computer graphics, we call this a scene. Or in the theater, when the play is divided up into scenes, but in computer graphics, we think of a scene as something like this. And our idea is it's going to be that what happened here was that a painter set up the scene, then a painter put himself in a certain position to look at the scene, and then the painter painted on the canvas what he saw in the scene. Okay. Okay. Now, the canvas that he's painting on is our frame buffer. Just, that's where, these are all pixels here. So we a lot of graphics is set up with this metaphor of a painter, because in fact a lot of the ideas in computer graphics came from painting. A lot of the algorithms that we're going to look at, one of them is called the painter's algorithm, and the projection algorithm was invented by Renaissance artists. So this idea of looking at a painting and thinking of what painters do is actually a real common metaphor for how to think about graphics. Now, in computer graphics, each of the objects in this scene is called a model, because we model the glass, we model the fruit, we model the jar. So we have these, we want to create the idea of there being all these objects in a space, and then we want to have someone that looks at them. Now, we're going to use a metaphor of a camera that looks at them. Now, a painter was using his eye to look at them, and then he painted on a canvas. A more modern metaphor is you have a camera, and you point the camera at the scene, and then the camera has film in it, and the light from the scene hits the film. And the film then is the frame buffer. The light from the scene hits the frame buffer, the film in the camera, and in a modern digital camera, it's called LCD, a liquid crystal display. The light hits it, and that's where the pixels are. So the pixels are inside the camera. So you point a camera at the scene. Okay, so we need a way to model the idea of a scene, the idea of a camera pointed at the scene, and the scene holding a bunch of objects in different locations. Okay, and in this scene, the table is an object itself, so all these objects are sitting on the table. The table is itself one of the objects in the scene. Okay, and you can have a more simple scene like this. You get a more simple scene that just has a few objects in it. Okay, so the idea is there's a camera pointing at a bunch of objects. The scene is the whole notion of the camera and the models in the scene and where they are in space. That's what we want to model, this situation of a camera in a scene and models in the scene. Okay. Okay. And the question is going to be, the hardest part is going to be, how do we actually model the objects themselves? We have one question is, how do we actually, that's where most of the work is. Most of the work is in modeling the objects themselves. Okay. Now, in this computer graphics system, the scene is going to be this package. The scene is actually a package. Okay. This is the object that holds everything. So when you have a scene object, you're creating a still life. You're creating a scene. Okay. And the scene is going to hold a camera. The camera is going to, now our camera to start with is going to be real simple. We're going to assume, let me draw a picture. I mean, here's a 3D space. Here's, oh. Here's an X, Y, Z axis. Gotta wait on that. Okay, here's an X, Y, Z axis. The way we're gonna coordinatize things for this class is the X axis is gonna go off this way. The Y axis is gonna be up this way. And the positive Z axis is going to be over here. Okay, and these are all the positive axes. Okay, now that means that from our point of view, the negative Z axis is pointing back here. And we're, that's going to turn out to be important. So the negative Z axis is down here. There's the negative Z axis. Okay. In almost every graphic system out there right now, the camera actually sits at the origin. So right there at the origin is where the camera is going to be. So the camera, we think of it as sitting at And what's funny is the camera looks down the negative z-axis, which is a little bit odd, but that's the way almost everybody in graphics does it. The camera's looking down that way. Okay, now eventually we want to make the camera move around because that's what real cameras do, but that actually takes quite a bit of work. So we're going to start with the camera, and this is actually the way OpenGL does it. OpenGL has the camera sitting at the origin looking down the negative z-axis. In OpenGL, in the famous OpenGL graphics system, you actually can't move the camera. The camera's always sitting at the origin looking down the negative z-axis. And we'll see how you mimic, and essentially you don't really move the camera, you have a way of mimicking that. Okay, so we're going to have a kind of a restrictive system where the camera sits at the origin and looks straight down the negative z-axis. Okay, so that's going to be our camera in the scene. The camera in our scene is actually going to be real simple. It always, for now, thinks of itself as sitting at the origin, looking down the negative z-axis. Okay, so if we look at the scene data structure, we'll see that the scene data structure has a camera object in it. So a scene data structure holds a camera object. And the camera object, we'll see it holds some parameters. Okay, we'll talk about, so the camera object holds some parameters. Okay, so and the camera's sitting here at the origin looking down. Now, notice that that's not very much like what a painter would think of. Painters or even photographers are free to move their cameras around, and we're going to be real restrictive for a while. The camera sits still and everything else moves. If you want something to move, if you want the camera to step back, you can't make the camera step back. You make the objects move away from the camera. If you want to rotate the camera to look in a different direction, you can't rotate the camera. You make all the objects move. Okay, so we have to move the objects. We never move the camera. And eventually we'll figure out a way to make this easier to work with. But at the beginning, it's going to be kind of tricky. The camera always sits here, looks down the negative z-axis, and if we want to move the camera farther from the objects, we actually move the objects farther from the camera. Okay, all right. So that's part of the idea. There's a scene. Actually, the scene you can think of as is this three-dimensional space. You can think of this scene as this three-dimensional space, and the objects are going to be placed in that space in front of the camera, or if you want, behind the camera. Depends how you want to think about it. The camera's pointed in that direction, so you're going to put objects in front of the camera back here. Okay? All right. Now, the objects that you put in space are going to be what we call models. So now you can have a bunch of models in space. So for example, I might draw a little cube. Like there might be a little cube here. Whoops, I did the wrong thing. I can draw real quickly. There's a little cube in my scene. Okay, so my scene's got a little cube in it, and maybe my scene has some other geometric shape in it. I could draw a little tetrahedron. So you can imagine drawing lots of little 3D shapes in your scene. Okay, so there's a tetrahedron. Maybe I can't draw very well, but you could draw, you could have a sphere in your scene. But it's a really lousy sphere. Okay, so you have a blob. Okay, so now each one of these will be a model. Okay. Now the question is, so the scene, now if we look at the scene data structure, the scene data structure holds a list of models. So the scene data structure holds two things, a camera and a list of models. Okay, so that's pretty simple. It's just thinking of itself as a bunch of things in space and a camera looking at them. Okay, right? Now, so then the harder work is going to be describing these models. What do we do to describe a model? Okay, and for now, we're going to describe models in what are called wireframes. Okay. You can just see pictures of them. Okay. Okay. So here's a real simple example. A cube was just, the idea of a wireframe is that you describe the model just with lines. You use lots of lines to describe a model. So here's a real famous example, a teapot. Okay. So notice that you can see the outline of it. The model's not solid. You're seeing through it because the model's actually at this point just thought of as a bunch of little line segments. Okay, that's going to be our main idea for representing models. Okay. Oh, and let me show you something here. Windows has got built into it. This is something new that's in Windows. They put this 3D model viewer in Windows. Okay, that that actually is a 3D model. That's a wireframe model. Let's see, how do I stop the animation? There. That's actually a wireframe model. But if I go over here and I look at view, if I remember where, there. See, you can see it's really just a wireframe model. It's just it really is just a bunch of little line segments. Now they've shaded in between the line segments, but the model is really a wireframe model, and then we'll see how you layer on top of it what they call textures. What makes it look real is that we're going to layer on top of the wireframe textures, but we start with a wireframe model. Okay, and in this picture over here, no textures have been added to this wireframe model because that's what we start with. And that's, if you look at graphics in the 1960s and 70s, that's all they could draw was wireframe models. So we kind of do things in a historical order. We start with the basics and work our way up. So if you looked at computer graphics in the 60s, it was only wireframe. Their computers weren't powerful enough to do these textures yet. The computers had to get better before they could do textures. So we start with the idea of a wireframe model, and then we'll layer on, later on in the semester, we'll layer the textures on top of, we'll layer the texture on top of the wireframe model, and then we'll actually get what looks like 3D graphics. Okay? So
Wait,
all computer pardon me?
Is there any difference between wireframes and polygons?
No. Well, yeah, polygon is another word for wireframe. See, polygon, the word polygon just means lots of edges. Poly meaning many, like a square is a fourgon and a pentagon has 5 sides. So polygon means multiple sides. But in fact, these things really aren't polygons. If you notice, they're all triangles. And same, like here, they're squares, and here they're triangles. And almost everybody uses either squares or triangles. Mostly they use triangles. But yeah, we call that, the fancy word for this is a polygon mesh. See, if I Google polygon mesh, the pictures I get are wireframes. See, so wireframe really is just like a synonym for polygon mesh. Okay. So polygon mesh is just a fancier word for the idea of a wireframe. This exact same picture shows up in the wireframe. When you ask for a wireframe, this dolphin is a real thing. You'll see the same models. This rabbit's real famous. It shows up all over the place. This dolphin shows up all over the place. The teapot shows up all over the place. The teapot was actually historically the very first model. The very first example of a graphics model was the teapot back in the 70s. This teapot's real famous. Okay, it's actually in, I think, the Smithsonian Institute. The actual teapot that this guy was modeling, I think they put it in the Smithsonian, I think. Okay, So you'll keep seeing the same models over and over again that people use all the time. So Polygon Mesh and Wireframe mean the same thing. And we're going to do nothing. We're going to stick to wireframes for a while until we learn enough that we can layer textures on top of them. Okay. Now, how do you build a wireframe? What is a wireframe really made up of? If you look, it's really going to be points that represent where the line segments start and then line segments connecting the points. So what we say is that a wireframe is made up of vertices, the points, and edges, the line segments. If I go back to this Microsoft thingy, here's the vertex count. Like this bug, he's got 29,614 vertices in them. Okay. Now, instead of counting the edges, they count the triangles. He's got 51,000 triangles. We're going to work with just edges for a while. We're going to keep things real simple. So instead of even working with we're really working with wireframes of just points, vertices, and edges, not vertices and triangles. We'll get to triangles a little bit later. Triangles are a little bit harder than just edges. So our wireframes will start out as vertices and edges. Then eventually they'll become vertices and triangles, or if you want, vertices and polygons, because sometimes people do use squares instead of triangles, but not very often. And then after you've got vertices and triangles, then you layer textures on them. And notice that they're still showing me the wireframe. If I turn off the triangles, then I get a better picture of the thing. Usually you don't show the underlying wireframe. If you Google around, you'll see that like even in a Pixar movie, all the characters that are in a Pixar movie are built up this way. Even it doesn't matter how elaborate they are; they're all built up out of triangles and vertices. And you can find pictures on the internet where they show you the wireframe structure of a model from Pixar movies, if you're curious about it. They can have hundreds of thousands of vertices and triangles. They can be extremely complicated. Like just this insect is 30,000 vertices. Okay. All right. So this is our idea. Now, what we're going to do with that is we go back over here. We want to look at what a model is. Okay. So a scene is a list of models. So let's look at what a model is. Excuse me. A model is what we just said, a list of points and a list of line segments. Okay. Now, you could just say, well, why don't you just have a list of line segments? Why don't you just say you have, why don't you just say, let's see, where's one of the other pictures? Why don't you just say, well, you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 line segments. Like this wireframe cube is 12 line segments. Okay, well, you could say that a model just is line segments, but then you'd still have to say for every line segment where it started and where it ended. Now think about, suppose I was going to make this model 12 line segments. So I'd have to say, okay, here's line segment 1. It starts here and ends here. Now, here's line segment 2. It starts here and ends here. Here's line segment 3. It starts here, it ends here. Does anybody see something that's wrong with saying it's a bunch of line segments? Anyway, line segment 1 starts here, ends here. Line segment 2 starts here, ends here. Line segment 3 starts here, ends here. As a programmer, what are you starting to see me do that's not a good idea? Oh, if somebody put it in a group chat. Yeah, you've got there's this point here that's being repeated. If I think of this as a line segment that starts here and ends here, I'm referring to that point. And if I think this is a line segment that starts here and ends here, I'm referring to that point again. If I think this is a line segment that starts here and ends here, I'm referring to that point a third time. So I've got that point in 3 line segments. And if I think of my model as 12 line segments, I'm going to be repeating every point 3 times because every point is in 3 line segments. So designers of graphic systems realize that that's not how you really want to do it. You don't want to say that a wireframe is a bunch of line segments. You really want to say it's a bunch of vertices and line segments. And we're going to organize it so that this vertex only appears in our model one time, because it's only in the picture one time. And we'll find a way to have this line segment, this line segment, and this line segment all refer to it. So we're going to use some object-oriented ideas, and we're going to use pointers and object-oriented ideas, and we're going to make this efficient so that this point doesn't have to be described a bunch of times. Now, if you think about this one, if I can't zoom this, but notice that every point is in 4 line segments. Every point is in 4 line segments. So you don't want to have that point appear 4 times. You really just want it to appear once. If you look at more complicated meshes, like look at that point there. He's in 1, 2, 3, 4, 5, 6, 7, 8 line segments. You really wouldn't want to say that there's a line segment here and a line segment here and a line segment here, and then have to repeat that point over and over again. It'd be nicer if you could just have that vertex, that there's this point in the model. Then have that line segment, that line segment, that line segment, that line segment all reference that point. So that's a more efficient way to do things. So we think of our model as, like I said, so we think of it as a list of vertices and then a list of line segments. Okay. So now what's a vertex? Well, let's look it up. A vertex is in the package. Vertex is real simple. It's 3 doubles. X, Y, Z. It represents a point in space. So that kind of stops things. This class holds references to primitive types. So we kind of end here. A vertex is 3 doubles. Okay. All right. So a model is a list of vertices, and the vertices are, each vertex represents a point in 3-dimensional space. Back to this picture over here, that's a point in front of the camera. Okay. We refer to those points as being in what we call camera coordinates. Okay, so the points are in what we're going to call the camera coordinate system. So the vertices in this model are in this X, Y, Z coordinate system, which we call the camera coordinate system, because he's at the origin. The camera's at the origin, so we traditionally call this the camera coordinate system. Later on, we're going to get a bunch of other coordinate systems. We're going to have the camera coordinate system, the view coordinate system, the model coordinate system, the clip coordinate system. And one of the things about computer graphics is you learn a whole bunch of different coordinate systems that are used to model the graphics pipeline. But it starts at the camera coordinate system. That's where the models, each model, its vertices are in that coordinate system. Okay? All right. Now, what's a line segment? This one's the tricky one. You know, how are we gonna model this idea of a line segment? So let's look it up. A line segment is an array of 2 integers. Okay, which is okay. Now here's how I want to go back and think. Here's the idea. Where's the picture of that cube? There's vertex 0, vertex 1, vertex 2, vertex 3, vertex 4, 5, 6, 7. Okay. Think of the vertices as being in a list. So there's vertex 0, vertex 1, vertex 2, vertex 3, vertex 4, vertex 5, vertex 6, vertex 7. So they're in the list. They have an index in the list. This line segment goes from vertex 0 to vertex 1. 0, 1 are the 2 integers that line segment stores. It stores the indexes into the list of vertices of whose endpoints are. So this line segment would store the numbers 1, 2. This line segment will store the numbers 2, 3. This line segment will store the numbers 0, 4. That's 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, 7. And I have a picture of that in the in render 1. Let's see if where is it? Under examples, there's an example of a cube. Okay, here's the picture of the cube. Okay. Here I put, I actually numbered it different than I did when I was going over here. You know, here's a cube, it's got 12 vertices. In this one, I numbered it this way. Here's the lower left, here's the, this cube, this corner of the cube sits at the origin. And I called that vertex 0. Go over on the bottom, there's vertex 1. Come forward to the front, there's vertex 2. Go over, back to the left edge, that's vertex 3. Then go up to the top and go in the same order, but around the top. 4, 5, 6, 7. Okay, so then this vertical edge here holds the indices 0 and 4. This edge here would hold the indices 4 and 5. This edge here would hold the indexes 5 and 6. Okay, so that's going to represent that model. And if you look down here, here's how I would do it. Create 8 vertices. There's the vertices in camera coordinates. Okay, there's the vertices in camera coordinates. Okay, now actually that's not, in a minute we'll see that this is actually really bad. If that's camera coordinates, I got a problem. Oops. Here's my picture of camera coordinates. Here's my picture of the cube. Does anybody see the problem? Here's my camera sitting there. We're going to start thinking, we're going to be doing lots of geometry. So you have to start thinking geometrically. The camera's sitting there looking down here. I put the cube here in camera coordinates. What's wrong?
It's not in negative z axis?
Yeah, it's behind the camera. First of all, it's sitting on top of the camera right there. The camera's right there, and then he extends behind the camera. How do you think I'm going to get him visible to the camera?
Move it.
Move it. We're going to have to write some code to move the cube to where we want it to be. Now, why would I do that? You know, why didn't I just put the coordinates in here of where the cube would be? See, you know, for example, this cube here is pretty far back. Maybe it's up a little and to the right. I could have programmed those right in here. Okay. Why do you think I did it this way? Sitting at the origin, going this way. The answer is because I want to be able to place this cube anywhere I want over here. And it's easier to start with the cube in a known easy place and then move it to where you want than to just hard code into the cube exactly where you think it's going to be, but then you find out, oh, that doesn't look good, I want to move it. So it's actually just it's like a practical thing. We almost always put our models sitting at the origin to begin with, which is not good because then they're sitting on top of the camera and they're usually behind the camera. But it puts our models in a place where we kind of know where they are, and then we will move them to be in front of the camera where we want them. So it's kind of just it makes it kind of convenient that way. It's not, I mean, I could literally put the 8 vertices here exactly where I want the cube to be in camera coordinates. But it turns out to be a little bit more convenient to model the cube in a known location, almost always at the origin. Almost all our, like when we model a sphere, we'll model it as centered at the origin. We put a cube, sometimes I'll put the cube centered at the origin, sometimes I put the cube with its corner at the origin. So we put our model at the origin, either just, like the cube could either be just touching the origin or it could be centered on the origin. Either one works. And then we go move it to where we want it to be. Okay, so that's just kind of it doesn't have to be that way. But so these are camera coordinates. We're in the camera coordinate system. But right now, if I took that model and rendered it, it wouldn't show up because it would be back here behind the camera. The camera would not see it. The camera only sees what's in front of it. Okay, so we use coordinates. When we first create a model, we almost always use coordinates that are just convenient. Now here's the line segments. Notice the line segments are things like 0, 1. That's the edge that goes from vertex 0 to vertex 1. So that's that bottom back edge. Then there's a line segment 1, 2. 1, 2 is this bottom forward edge. Then there's a line segment 2, 3. Still, see, I kind of commented that we're on the bottom face. 2, 3, the front bottom face. This one's the left edge of the bottom face. Then there's 4 that go around the top face. And then there's 2 line segments that are the vertical back face. See, 0, 4, 1, 5. 0, 4 is this vertical edge in the back face. 1, 5 is that vertical edge in the back face. And then the last 2 are the vertical edges in the front face. Okay, so that's how we structure geometry in graphics. Later on, instead of doing vertices and line segments, we'll do vertices and triangles where each triangle has 3 edge corners. And then we'll be ready to layer, then we'll be doing this kind of thing. Okay. So we'll eventually get to vertices lumped together as triangles or polygons, though people actually, when they use the word polygon, they almost always mean triangle. And we'll see for technical reasons, triangles are way better than any other kind of polygon, like quadrilaterals or pentagons. So triangles are the best polygon. Okay, so we will eventually move from vertices and line segments to vertices and triangles. Okay, and then a triangle will be a list of 3 integers, which give you the 3 corners of the triangle, but it'll still be the idea that you'll have a big list of vertices, and then you'll have a list of triangles, and each triangle will tell you which 3 vertices it uses, and that way I don't have to keep repeating a vertex. When a vertex appears in, like this vertex here appears in 1, 2, 3, 4, well, as edges, that vertex appears in 1, 2, 3, 4, 5, 6 edges. As far as triangles is concerned, that vertex is in 1, 2, 3, 4, let's see, is it 6 triangles too? Yeah, he's in 6 edges, or you can think of it as being part of 6 triangles. We don't want to keep repeating that vertex. We would rather just say that that vertex is in the model, and then that 6 triangles share that vertex. It becomes much more efficient that way than to say that a triangle is 3 vertices. If we said a triangle is 3 vertices, which some rendering systems do it that way, but it's not a good idea because it's too inefficient. If you say that a triangle is 3 vertices, then that triangle holds a copy of that vertex, that triangle holds a copy of that vertex, that triangle holds a copy of that vertex, and you end up with a very redundant. Now, we'll see that occasionally you do want to do it that way. And if I do want every line segment to hold its own copy of a vertex, and I can do it in this case. Let's see, where's my picture? If I really wanted that edge and that edge to have their own copy of that vertex, here's a reason why I might do that. Suppose this is a box with a lid, and the lid can come off of the box. Well, if the lid can come off of the box, that means I really have 2 vertices right there. one vertex for the box and one vertex for the lid. When the box is closed, those two vertices are sitting at the same place. But then if the lid should lift up, I really need another vertex there to be able to lift the lid. So we'll see that sometimes you do want to have multiple vertices. You do want things to be redundant, but not always. Like if this box doesn't come apart, there's no reason for me to have more than one vertex to represent that point. But if that box is a lid that comes up, or if the box, you want the box to unfold and fold open, you might actually need more than one vertex to represent that point so that you can unfold the box. So now, nothing would stop us from repeating a vertex in this list. See, I could just take vertex 0. See, here I declared the vertices. In here, I put them in the list. I could put vertex 0 in the list more than once. If I wanted to be in there more than once, there'd be no reason why I can't put it in there more than once. Now it's appearing as index 0, index 1, and index 2. And if I wanted, I could have a line, I could have this line segment, this line segment, and this line segment each have their own copy of vertex 0. I have to keep track of which are all the vertex 0s. It gets complicated, so I have to remember that this one, and this one are really the same vertex, but they're 3 copies of the same vertex. But then I could, for example, move one of those. For example, suppose I wanted to make that edge fan out, but I wanted this edge and this edge to stay put. If I wanted that edge to fan out, but these 2 edges to stay put, I need a second vertex. I need a vertex for this edge to use, but not these 2. So I can do all kinds of funny things. There's nothing to stop me from putting a vertex in the list more than once. But then I have to keep track of all that. Okay. Right now, I'm doing it real simple. Each vertex is in the list a single time. Okay. So, oops. So our scene is a camera and a list of models. The model is a list of vertices and a list of line segments. Vertex is 3 numbers. Line segments 2 indices into the list of vertices. If you go back here to the README, I drew a picture of that just to help you remember it. See, here's the picture. It's a tree. Notice that we're starting to use data structure terminology, and this tree is going to get more and more elaborate as we go along. A scene is a camera and a list of model. You can think of these models as the nodes under a tree. If you think of this as a tree, usually people would just draw the scene as holding those models. Yeah, I'm showing you. So I'm showing you that the scene holds a list of models. The list of models, that essentially makes the tree the scene, the root of a tree with these 3 branches, and that 4th branch too. Okay, right. So a scene is a camera and a list of models. Now there's 3 models in that list. Each model is a list of vertices and a list of line segments. Of this list of vertices, I pretended it holds 2 vertices. Each vertex is an XYZ and XYZ, and each line segment is an array of 2 ends. When we get to triangle, this will be a list of 3 ends. Won't be much different. Yeah. And then we can have a list of triangles, and we could be doing much more 3D. Eventually it'll start looking like this. Not a big change. Notice it won't. There'll be the algorithms will need to change a lot. The structure of the scene won't change much when we go from wireframes to these polygon meshes. When we go from wireframes to polygon meshes, we'll change from line segment to triangle. This doesn't look like it's changing a whole lot, but the algorithms will change a lot. When we switch from line segments to polygon meshes, the algorithms get much more sophisticated, much more sophisticated. Okay, okay. So, and then the big thing is when we want to do when you switch to the polygon mesh, you want to fill in these polygons, like they did here. We'll want to fill them in. And that's the reason we switch from line segments to polygon meshes, because the polygon meshes let us have an easy way to fill in these pixels, just like they're doing there. I'll want to fill them in. when we do a real wireframe, I guess the real difference between a polygon mesh and a wireframe, the polygon mesh is filled in, the wireframe isn't. The wireframe just is the line segments. It just is this picture here, where you can see through and see inside and see through it. It's just the line segments. Okay, so the model doesn't change much when you go from line segments to polygon mesh. It's just going to change. You know, we're going to change line segment, which is a list. Each line segment's 2 indices, to triangle, which is 3 indices. Yeah, not a big change here, but then the algorithms will change, because once we have those triangles, we'll want to fill in all the pixels inside of a triangle and draw all those pixels, shade in all those pixels inside. And that will change the algorithms a lot. Okay, all right. So this is our structure. Now let's just look at some examples. Let's go back to this cube. Okay, so this is a real simple example. Okay. This will actually draw a picture for me. So what I do to make it a complete program, I instantiate a scene object. So that's the root of the tree. Yeah, I create that object. I instantiate the scene object. I only want one model in this scene, so I instantiate the model. I add it to the scene. Oh, the scene instantiates a default camera for you. Right now, the camera is real simple. So when I instantiate the scene, I get a default camera. Okay, so you don't see in this code creating the camera object, because the scene instantiates a default camera object. It instantiates an empty list of models, but it instantiates a default camera. We'll say a little bit more about what the camera is, okay, later. So I instantiate the scene and I get a camera for free. I create one model and I have to add it to the scene. So scene.add model. Okay, so that puts that model, that puts one model in this list of models. So our scene's going to have a camera and only one model. Okay, all right. Then I instantiate a bunch of vertices and then I add them to the model. Okay. I can write this 2 ways. I could add them as I'm instantiate them, or I could instantiate them and give them names and then add them by name. You'll see I do it both ways as we write the code. So here I actually gave each vertex its own name. Sometimes it's nice to have a name for each vertex. Sometimes I could do, if I wanted to, let me just show you what the other way would look like. Let me do this. I'll modify this a little bit and you'll see what I'm doing. I can just add the vertices as I build them. And a lot of times that makes for more compact code. So in this way, I don't give them specific names. I mean, I can always refer to them by their index in the vertex list, but I can just, and if I do this, I change the semicolons to commas because I'm building a list. And I put another parentheses there. Okay, and then I don't need this line of code here. Okay, sometimes I do it that way, sometimes I do it the other way. It's kind of 6 of one, half dozen of the other. Which style do you like better? I'm instantiating the vertex and immediately adding it to the model. Yeah, and I'm instantiating that vertex and just immediately adding it to the model. I'm not giving it a name. If I need to refer to it, I can refer to it as index, like this vertex is index 2 in the model, so I know how to get at it. But yeah, if I don't care about giving it a specific name, I can refer to it by its index in the model. Okay, so either one works. You can just, now notice that down here I added the line segments in that style. I just instantiate a line segment and add it to the model, add it to the list of line segments in the model. So the model class has an add line segment method that takes entry and puts it in the list of line segments. Okay. So you can do it in either style. Okay. You can use the style of instantiate the objects, then add them all, or you can use the style of adding them as you instantiate them. Okay. Now here's where I have to move that. I have to move that model away from where it was. We put the model. We put the model in a bad place. The model's sitting here in front of the camera. You know, this coordinate system is this same x. This x, y, z coordinate system is this x, y, z coordinate system. The camera's right there staring down the negative z axis, so it's not going to see this cube. Okay? So I need to push the cube back. And the way I push the cube back is I'm really just going to, what I'm going to do is I'm going to take every vertex that's in the model. So I iterate through the list of, see, I'm going to write a loop that iterates through the list of vertices. It gets a vertex out of the list, and then it replaces that vertex with a new vertex that's been pushed back. What I'm really doing is I'm now just going through this list and deleting every one of these vertices and replacing it with a vertex that's got -2 there. Now, this is kind of dumb. Why did I create all these vertices and just immediately replace them? We'll learn a better way to do this later on. We're going to use linear algebra and matrix algebra to make this way better. But to keep the amount of code down, we're going to do things kind of in a dumb way until we get to the smart way, but the smart way takes a lot more code. So right now, the model is sitting here in front of the camera. I want to push it back, and I push it back by replacing all its vertices with vertices that are, well, see, every new vertex will have the same x coordinate as the vertex it's replacing, the same y coordinate as the vertex it's replacing, but its z coordinate will be 2 units back. So I'm pushing this cube back 2 units. So in this picture here, the cube's going to be here at -2 on the negative z axis. Okay, it's kind of quirky. You know, but not, I could have just put -2's in here, and then I wouldn't have to push the model back. I could have just put -2's and -3's. -2's for this and -3's for this. Actually, no, these would have been the -2's. -2 for this one and -3 for this one. Okay, I could have pushed them back, but this is the more general way to do it. Because what I want to do is create movies and things like that. I want to create movies where objects move around. So I want to get used to the idea of moving an object around. So instead of hard coding him in front of the camera, I really think it's nicer to put him in a known location and then push him back. Again, you iterate through the list of vertices, you get the vertex, then you replace it by setting in the list a reference to a new vertex. Okay? So these vertices are actually replaced. All these vertices are going to be gone from the list. The reference to that vertex is replaced with a reference to a new vertex. What happens to the old vertices? What happens to these? When I replace their references with a reference to a new vertex, what happens to the old vertex? What happens to an object when you don't have a reference to it anymore?
Garbage collected?
Garbage collected. And if we were doing this in C++, in this loop, I would have to free, if this was C++, I would need a line down here that, see, I'm glad this isn't C++, but if it was C++, I would be freeing that vertex that's not being used anymore. And if I didn't, I would have all kinds of problems. So that's the beauty of Java versus C++. In C++, you better keep track of who's allocating and who's unallocating all your memory locations. Java has a garbage collector. So right now, after I do this set, this vertex here is not being referenced anymore. It'll have been replaced in this list by another vertex. So if this was C++, I would need to free the vertex that's no longer being used. Otherwise, it'd sit there in memory forever. And after my animation had run for a while, I'd run out of memory because I would have thousands and thousands of vertices sitting in memory that aren't being used anymore. Java will keep cleaning up memory for you. Okay, so I'm relying on the fact that Java frees the Java garbage collects these unused vertices for me. Okay, so Java is a beautiful language, and this is one of the reasons why not freeing memory properly is one of the biggest sources of bugs in C++. It's not a trivial matter. Knowing how to free memory, who's responsible for freeing memory, when should you free memory, is a huge problem in the C++ language. Okay, for example, this would be a mistake. Depending on how I did this, this would be a mistake. Let's see. Well, it depends. Notice that every vertex is shared by 3 line segments. So if I'm not careful, if I free this, I could free a vertex that's being shared by some other people. That's why freeing is real hard and complicated. Because if a vertex is being shared by 3 edges, and if I free it from one edge, I may not be supposed to free it from both edges. So I have to keep track of whether it's still being used by one of the other edges. So this is why C++ is so much more complicated than Java. In Java, if I've got this vertex shared by 3 edges, and this edge gets its own vertex, how do I know if I should free that vertex or not? In Java, I don't care. I let the garbage collector figure out if that vertex is being used or not. So C++, and if I took this edge and stuck it out this way, and I no longer use that vertex, but I use some other vertex, I would have to keep track of myself of, oh, is that vertex now free because no one's using him? Or is that vertex still being used by 2 other edges? That's a monumentally hard problem. And in real graphics written in C++, huge amount of effort is going into keeping track of whether vertices are still being shared by some edges or not. When one edge stops using a vertex, you got to know whether other edges are still using the vertex. If no other edge is still using the vertex, you free it. If some edge is still using the vertex, you don't free it. That becomes hard sometimes that some people don't ever share vertices. They go back to what we were talking about a little while ago. They make every edge, they would make this vertex literally appear 6 times in their code so that if they want to move that edge, they don't have to keep track of whether that vertex is shared or not. Sometimes people get lazy and they just duplicate their vertices so they don't have to keep track of whether they're shared or not, which then causes its own problems because you start using huge amounts of memory. Java actually, by keeping track of the sharing for you, by doing the garbage collection for you, actually makes programming way better. Okay, so since we are sharing vertices between edges, Java keeps track of when our vertices really aren't being used and when they still are being used, and that works out really well for us. Okay, so it's Java, so I don't have to worry about freeing the vertices that I'm not using anymore. Okay, now once I push the model back, I can start rendering. I render by creating a frame buffer. Okay, so I'm going to create a 1000 by 1000 frame buffer. Okay, and then I'm going to make the frame buffer dark gray, do some other stuff. Then here's the key idea. I'm going to render the scene into the viewport of the frame buffer. Okay. Later on, we'll see that we can render, like, picture in a picture, like on a TV set. We render not into the frame buffer, we render into a viewport of the frame buffer, because it's sometimes nice to have a frame buffer set up with multiple viewports and do picture in a picture. We can render into, you see that in games all the time. When you have like a heads-up display in a game, that's a viewport in a frame buffer, and you can render a scene into the little mini display. So you can have multiple viewports in a frame buffer. So the render actually renders scenes into viewports. Now, right now, I'm using the default viewport, so it's the whole frame buffer. So I'm actually rendering the scene into the whole frame buffer, because that's the default viewport. Then after I've rendered the scene into the frame buffer using the rendering algorithms, which we'll talk about next week, then I can dump the frame buffer to a file and see my picture, okay? And then actually what I want to do is I want to create a movie. I create a movie. Let me see. Now, let me run this program, show you what I mean. I'm in this folder now of examples. And this is the offline cube example. So I want to run it. I compile it and run the zip file. That thing compiles and runs it. Now, when it runs it, it's actually creating tons of view. What it's doing is it's creating a bunch of frame buffers and storing them. And what they're doing is creating a movie of this thing moving. Kind of quirky movie. I'm going backwards. Wireframe view is kind of nice. Every time I hit the space bar in Wireframe view, it moves to the next picture in the sequence. And if I just hold the space bar down, it looks like I'm watching a movie. Wireframe view is real convenient at doing this. Wireframe view always does the right thing. It's a great program. So if I just hold the space bar down, it actually shows it as if it was a movie. Later on, we'll see that we can actually take these frames and use a piece of software to turn them into an actual movie. These are the frame. That's why we call them frames. Why we call it a frame buffer. Each one of these frame buffers stored as a picture is a frame of a movie. And then we'll use a piece of software that's going to convert all these frames into an MP4 movie. Okay. So right now we can, Wireframe view kind of fakes it being a movie by letting us. If you look up here, you see that I'm stepping through the frames. There's frame 26, 27, 28, 29. And down in the code, what I did was render the scene into the frame buffer, then start up a for loop. What the for loop does is it does the same thing I did over here. It moves the model by replacing all his vertices. For each iteration of this loop, I'm going to take every vertex in the model and move it to the right 1/10 of a unit. So every vertex is replaced with a vertex that has the same y, the same z, but a little bit different x coordinate. So every vertex is used to replace it. It's replaced with a vertex that's slightly different than it. Okay. Now notice that I'm changing the vertices. I'm not changing the line segments because the line segment structure is always the same. I'm not going to touch the line segment structure because my cube never changes its shape. I'm just moving the vertices. So the line segments always keep their same structure. It's the vertices that move. So this is a very nice structure to the idea. When I want to move it, I move the vertices. Okay. In OpenGL programming, this is what might be called a vertex shader. Okay, this loop here is what you may have heard of vertex shaders. I'm moving the vertices. I'm not touching the line segments. The line segments refer to the vertices, but the cube isn't changing its shape. So when these vertices all move, the line segments still have the same relationship. Okay, so then after I've moved all the vertices, I clear the frame buffer so that it's blank again. Render the scene, which has now got a new model in it, into the viewport of the frame buffer and save it as a new image. Notice that I'm using string format. I'm interpolating this number into the name of the file. That's how I get the file names. That's how I get these file names 0, 1, 2, 3, 4, 5, 6. It's a nice, I'm using the string format. I could also use printf, but this was easier to do it this way. Okay, actually printf doesn't work very well for this. There is no string printf in Java, so you have to use format. So I'm formatting the string with, see, there's the thing that interpolates this guy into the string. Okay, so I'm creating these file names based on the iteration of the for loop. So then I get these pictures. Each one's a little different. Notice that this guy is going off the right edge of the screen and he's wrapping in on the left edge of the screen, which is flaky. And we'll see in a little while how to fix that. But really what's happening right now is here's the picture. Here's the cube. He starts off, he's just barely in the frame buffer. One edge of the cube is on the edge of the frame buffer. He's moving to the right, so he falls off the edge of the frame buffer. He wraps to the left side of the frame buffer, which is not a good thing, okay? I can prevent that by going into my code and turning on what's called line clipping. And this is one of the algorithms, and we'll talk about it, but here, do line clipping, set it equal to true. I want to tell my algorithm to clip off lines that fall off of the screen. Then if I compile this and run it again, I can clean up the ppm files.
Wait, I think there's no way to prevent those messages from popping up.
Yeah, there is. Somebody sent me an email about it, and I forgot to go do it. Somebody sent me an email telling me how to fix it, and I forgot to go do it. It's what what is it? Does anybody remember? What is it? You go somewhere?
No, I think about there's these programs that convert batch files to exes, and maybe that might be like a band-aid solution to it.
Well, now watch. See, if I do this again, I don't get that pop-up. It only happens the very first time I do it. Okay, so you only get that, like here, I'm going to clean the class files. See, I get the pop-up only one time, and then Windows remembers, and so then I don't have to do that again. So I only get the pop-up the first time I double-click on one of these. So it's not very annoying. So that's why I'm not turning it off globally, because Windows remembers that you dismissed that pop-up. Okay, so now, for example, if I take this cube and I run it again, I won't get that pop-up. Now this is running it with the clipping turned on. Now when he goes off the edge, there's nothing wrapping. But now he's off the edge, and the rest of the movie, he's not in the frame anymore. Okay, so you don't see him in the frame anymore because he went off the frame. Okay, so he's completely off the frame. So one of the algorithms we're going to learn is the clipping algorithm. The clipping algorithm is the algorithm that says when something goes off the edge, we should cut it off so that it's somehow, and we'll see why it wraps around. Like if I don't clip it, why did it show up over here? So when we talk about the algorithms, we'll talk about what we mean by clipping and why when this line segment went off this way, it showed up over here if we didn't clip it. Okay. All right. So, oh, we're almost done. Okay, we got a couple more minutes. Okay. So that's the idea of this is our simple. Now notice I call this offline rendering. This is what Pixar does. Pixar generates a scene, stores the scene, and then goes and generates another scene and stores the scene. That's not what your games do. Your games are online. They're interactive. They're not offline. Now, why is a game interactive? Why are Pixar movies interactive? In a real Pixar movie, the frames are so elaborate that they take something like an hour to compute. The amount of work it takes to generate one of these frames is something on the order, I think, these days of an hour. And a movie is 60 frames a second for an awful lot of seconds. So there's millions of frames, and these frames take upwards, they take a long time to render. In a game, you want 60 frames a second, and you want the frames to generate every 60th of a second. That's why your games don't look as nice as a Pixar movie, because there's just no way a single computer can generate the frame of a Pixar movie in 1/60th of a second. We don't have computers that fast yet. Maybe by the time you guys pass away, before you pass away, you'll be playing a game that looks like a Pixar movie. probably well before you pass away. It's coming along pretty quickly. But in maybe 10, 15 years from now, we will have games that look as nice as Pixar movies. But right now, we still don't. A Pixar movie is an offline rendering system, like this. Now, this can be done. My computer's fast enough to do this online. Let me show you. There's another renderer up on the website. Got a couple minutes. Let me just show you real quick. Here's another render that's interactive. And we're going to use it eventually we're going to learn how it works. But right now, I just want you to use it to play around with. Like, this is now an interactive render. This render takes keyboard commands, and you've got a little window here telling what the keyboard commands. For example, the slash key switches me between models. Here's a bunch of different models. Okay? These are all the different models the renderer can render. The X key makes the model move left and right. The Y key makes the model move up and down. Oh, if I move the model off the left edge, he shows up over here. Now I need to turn on clipping. The C key turns on clipping. You can see over on the left that I say clipping is turned on. Now that model is being clipped, and notice if he goes off the screen, you don't see him anymore. But if I turn clipping back off, there he is, but he's wrapped. That's a weird version of the cow because he's really way over on the left, but he's wrapping, which he shouldn't. Okay, so you can play around with these models in an interactive way. Eventually, we want to be able to rotate models, but we don't have that yet. Right now, we can only make models move up and down, left and right, and I can make the model move farther away from me. Notice how he shrinks if I make him move farther away, and he grows if I make him move closer. Right now, we're using a perspective camera. I can switch to what's called an orthographic camera. And then if I use an orthographic camera, we'll talk about that in a while. I can't make the cow can't move backwards. Orthographic camera is a different kind of camera. So there's two kinds of cameras. See over on the left, I'm using an orthographic camera projection, or I'm using a perspective camera projection. When we talk about the algorithms, we'll talk about these two different kinds of cameras. So what I'm switching there is between two different kinds of cameras. And let's see, what else can I do?
Professor, I have a question.
Yeah.
It's not so much about graphics, but about Java in general.
Mm-hmm.
So when you press the key to move up, down, left, and right, when you hold it down, does it pause a little bit, then move?
Yes.
Is there a way to fix that?
No, that's part of that's the way the operating system works. The repeat key doesn't kick in until there's a slight pause. Oh, there is a way to fix it. In your interface, let me see if I can find it. Look up the control panel. Go to, I think it's in here on the keyboard. Repeat rate, repeat delay. See? The repeat delay is how long you have to hold a key before it starts repeating. So where's my text pad? If I hold down the Z key, notice how there was a slight delay before it started repeating. See, I'm gonna press the Z key and hold it.
I see it.
That slight delay is set by this parameter in the control panel, the repeat delay. Right now I have like here, I'll give it a long delay. See, I think it takes effect right away.
Yeah.
Yeah, now I hold down the Z key, see how long it took to repeat. Okay, so you have control over that. Most people, the default is about right. I think it was, I hope I get, yeah, okay. A shortish, and then you can control how fast the repeat is too. The repeat rate you can set it. That's got nothing to do with Java. It's part of your operating system. Yeah,
Gotcha.
Yeah, so Java is getting the keystrokes from the operating system, and the operating system controls the keystrokes. So it's got, and now there might be a Java library that can set that parameter. You know, if somebody knew a lot more about, like if somebody's a game programmer, they might know that, you know, a game might want to allow you to set that parameter from within the game. So maybe there's a library. Well, yeah, I'm sure there is, because Windows has a library parameter. There is a Windows library function to set that parameter. So you could expose it through Java. You know, Java can call any Windows library function it wants. It's just tricky, but Java can call Windows library functions. I've never done it. I've actually never written Java code to call Windows library functions, because that defeats the purpose of writing platform independent code in Java. Okay, but whatever. So that repeat key that I'm using it here when I want to move this guy here. I just like here, I'm just holding the X key so that he slides along. Notice he doesn't slide very fast. What's funny is when I switch between models and I hold down the repeat key, the models switch really super fast. I'm not sure why they slide so slowly, but they switch real fast. I haven't really kind of figured that out. They switch real fast here, but they move left and right. Let's see, that's not. They move kind of slowly, but they switch very quickly. Whoops. I forgot to turn clipping on. When you don't clip, sometimes the pixels go off of the frame buffer and you get these bad frame buffers. Let me just show you one last thing. Let me go to, okay. Here's clipping off. Here's clipping off and clipping off. Okay. Now, notice that there's nothing really wrong going here. If I go off the top, we're going to talk about this a lot later on. If I go off the top edge without clipping, the renderer crashes. The top and bottom edges are not the same as the left and right edges. You don't get wrapping on the top and bottom edges. And that's actually kind of an interesting question. We'll have to talk about why that is. So the left and right edges, when you don't have clipping, they wrap around. But the top and bottom edges crash. See, I'm getting frame buffer bad pixel messages. The frame buffer is actually crash. It's not crashing. It's getting index out of bounds errors, and I'm catching them in a catch clause, and I'm catching them as errors. Okay, so we're going to talk about that. So when you turn off, if you don't have clipping turned on, the top edge and the bottom edge don't wrap, they crash. The left and the right edges wrap, and we'll talk about that. Now we've run out of time. So anybody got any last minute question? You know, we've introduced the idea of the scene class. You know, we've gone through the rough idea of the scene class. Read the README for the scene class. Oh boy, I'm lost here. That's render 2. We haven't talked about render 2. Where's my desktop? I got too many windows open now. I'm getting lost. Okay. Read this README. Okay. It describes the render. And if you build the Java docs, that README is formatted kind of nicely here. So it's a little bit nicer to read. If you want, you can read it as a web page, or you could read it as a text file. Okay. All right. So we've gone through the basics here. Does anybody have any last question? Is there any question about what we've been talking about today? if you want to play with Windows 3D renderer, this is a weird thing they added to Windows 10. There's this 3D viewer, and there's also there's a program that comes along with it, 3D Paint. I think it's on here. There's 3D viewer and 3D Paint 3D. I'm sorry, it was Paint 3D. So they built two programs into Windows 10 that let you build 3D models and play with 3D models. Okay. So there's a whole bunch of I forget where they are. There's a whole bunch of built-in models in here. But this is a program that actually lets you build 3D models. So they've got a 3D model viewer and a bunch of models built into it. And then they got a 3D model builder that you can build your own 3D models. Okay, so that's kind of cute that's a feature now of Windows 10. I'm not sure how many people actually use it, but it's kind of a weird feature that Microsoft thought would be. It's got to do with the HoloLens, their 3D virtual reality product. They built these programs into Windows 10 to try to pair them up with the HoloLens thing. I think they thought people were going to be buying HoloLenses like crazy, so they wanted this built into Windows 10. Okay, so you can play around with some nice 3D models in Windows 10. I think everybody's Windows 10 comes with the 3D viewer and the Paint 3D program. Anybody got any last questions? Any questions about what we've been talking about? If anything comes up, please send me an email or come to office hours. And let's see. So I will stop sharing and then end the meeting here. Play with the 3D, play with the interactive render. I put it up there. We're not going to talk about the interactive render for a while, but it does let you kind of see just what the render can do so far. Okay, so I'm going to stop the sharing and end the meeting. So let's see. Remember, Monday's Labor Day, so there's no school on Monday, but we'll have class on Tuesday. So see you on Tuesday. Bye.